So as the title says, today I'm going to talk about the use of structural health monitoring to support decision making on the vertical lift bridge. Here's the outline of the presentations. First of all, I would like to give you a brief introduction to structural health monitoring and the need for decision making for vertical lift bridges. Then we will take a look at the monitoring program for the Memorial Bridge in New Hampshire. And to end up with this presentations, I will take a look at the future works and conclusion of this work. As this slide shows, the principal steps behind structural health monitoring postures is somehow similar to concept behind body analogy used in medical sciences and technology. In both cases, the main step is to use the appropriate use of the tools and equipment for the overall health monitoring of the structure or, for example, the overall health of the patient. And the aim is to implement and rehabilitation activities in case of any excessive stress or deformation on the structure, which is the same in medical sciences if any symptoms of diseases is observed. In addition, the structural health monitoring works similar to nervous systems in humans, which is good at alerting if abnormal events is observed. And in the context of structural health monitoring in civil engineering, the SHM is defined as implementing damage detection procedures to efficiently monitor the behavior of the structures over time and extract damage-sensitive features that are useful to determine current states of the structure. It has many benefits and advantages. For example, it will increase the safety and serviceability of the structure and minimize the maintenance costs and increase the life cycles of the structures, can detect hidden damage in the structure and also detect potential capacity of the structure. Bridges are generally monitored by the predominance of visual techniques. Over the years, these techniques are combined with non-destructive techniques to increase the efficiency of monitoring system. However, these suffer from some serious limitations, in which they depend on accessible portions of the structure, which sometimes is not easily possible during practical cases, in real cases. They require large amount of human interventions. They are costly to continuously monitor specific structures, and more importantly, they need prior knowledge about the proximal locations of damage. To overcome these limitations and to improve the monitoring systems, global monitoring systems have been improved to monitor the behavior of the structure at a few easily points. And in this case, the ideal structural health monitoring system is a system that could evaluate the performance of the structure with almost no human interventions. For example, use the ambient excitation sources to vibrate the structure. Among bridges, vertical lift bridges are very important, and they provide a unique opportunity for engineers involved in the structural condition assessments, because they provide a valuable source of excitations that can be used to vibrate the structures and use the ambient excitations to measure the dynamic response of the structures. However, in typical coastal zones in areas in United States, they experience significant wind conditions under variable temperature levels, and which call the need for health monitoring of these types of structures. In addition, there are few objective protocols for decision making of these bridges, subjected to different traffic loadings and environmental conditions. The Memorial Bridge is one of these vertical lift bridges that has been considered for structural health monitoring at the University of New Hampshire. This bridge is newly reconstructed and replaced on the original Memorial Bridge, which was demolished in 2012 due to structural concerns. And this bridge is open to traffic in July 2013, and it includes an innovative Gussetless connections, which is the point of interest for engineers to assess and validate design assumptions of these connections. A group of researchers and scientists at the University of New Hampshire with different expertise and from different fields, including civil and environmental engineering, mechanical engineering, ocean engineering, and computer and science, are incorporating together to provide smart, sustainable, and monitoring systems which will provide an automated system to monitor the behavior of the structure. This bridge contains different types of sensors that are deployed along the south span of the bridge, like structural monitoring sensors, marine sensors, and weather stations. Also, there is a turbine, Tidal turbine platform that is installed on one of the piers of the bridge with an aim to provide and supply the power of sensors in the future that makes and enables us to transform the memorial bridge to a living bridge that can continuously monitor the behavior of this system and bridge. The main objectives of this study is to verify design and performance parameters related to the Gussetless connections in this bridge and monitor the behavior of towers during vertical lift operations under a range of environmental loads, and also develop an objective lift or no lift decision protocols for lift operation in condition with bridge managers. Real-time data are continuously recorded and measured on the bridge, and they are stored on the server or the core that is permanently installed on the bridge. And the researchers at the university with access to this data through a controlled password controlled website. This website also has public site, which is but which is accessible for publics. They will see latest news, the current research activities, the photo galleries, and everything about this project. The important part is, after extracting data, is to transform them into meaning informations. Different types of sensors that are used, and they can be used for different purposes. For example, for life assessment and to assess the remaining service life of this bridge, for design verifications, for providing and to maintenance schedules, and also calibrate the structural models that are used to be optimized and updated with collected data, monitoring data on the bridge. The instrumentation plan has been done in two different parts. To design a long-term monitoring plan and to demonstrate potential value of a permanent installed systems, first of all, in fall and summer 2015, the short-term sensor deployment is introduced. In this presentation, 3 locations are considered for to show this to measure the response of the structure. Area 1 shows 2 types of sensors. The strain gauges and accelerometers are deployed to measure the response of the structure. Area 2, which is used to measure the maximum strain of the tower during lift events, and area 3, uniaxial and biaxial accelerometers were applied to measure the vibrations at the top of the tower during lift events. This is a typical example of the track passage at the mid-spans of the bridge on the top chord. Here we will see that the maximum strain and maximum acceleration response occur when track gets closer to the sensor. These types of information can be used, for example, the strain data to assess the remaining service life of the structure, and also the acceleration response shows that there is a significant impact on the acceleration response, the moving loads, and can be used to extract global parameters like natural frequencies and mode shapes, and to measure for future conditions assessment of the bridge. Vertical impact also has significant impact on the tower and the response of the accelerations on top of it. What is of interest here is the peak impact, like lift impact as shown in the rectangular, which is significant compared to other information that has been shown here. These kind of impacts can be used as a natural source for the excitations, and we can use this impact to vibrate the structures and analyze the response of the system. We have also developed a multi-scale modeling approach, which is used to combine both benefits of finite element tools and wire models of the systems to locally analyze the response of the structure, and it predicts its response due to different loads in critical locations. Also, to update this model for comparison with real monitoring data. With the result from the temporary data collections and the response predicted by the structural model, a long-term monitoring plan is developed in September 2016. Different types of sensors are selected and installed permanently on the bridge. And for example, for the south span here, you will see that 2 uniaxial strain gauges are used, 10 strain rosettes are used which measure the strain data in 3 different directions, and 10 biaxial accelerometers are installed through the top course of the bridge. In the tower, we have also used weather stations to measure the environmental variation like humidity, wind speed, and tilt meters are also installed to measure the rotations of the tower, and also there are strain rosettes and biaxial accelerometers on the bridge. Different studies are done with researchers at university. This is a statistical investigation for validation of the response of the strain gauges on the bottom chord of the south span. As shown here, for the classes of sensors on the bottom chord of the span, south span, you will see that the response of the strain gauge D is deviate from other sensors. This figure shows the bubble plot, which means the data recorded during 3 months of monitoring from the bridge, and density plot and box plot also confirms this difference. These types of information shows that these sensors, but they don't show good results, can be removed from the analysis in order to obtain reliable results. This slide also shows that temperature has a significant influence on the strain response. However, the average difference between the temperature in cold weather and hot weather shows that this difference is not constant for different clusters that are used on this bridge. So it means different factors can, like wind factors, other factors can affect the response of strains data. The other example is the acceleration trends of the bridge in July 12th, which shows an acceleration response and also the right mode strain data for different locations of the tower, which are measured during one day, 24 hours. And the low magnitude of the acceleration response here shows the low rating loads overnight. And for the strain gauges, you have the maximum minimum strain response, which reached to its minimum magnitude overnight. We have a typical example of the result of the tilt meters on the top of the bridge, which shows the lift events has a significant impact on the rotation of the tower on the top sides of the bridge. The influence of the wind loads are also considered in combination with the temperature. The maximum base wind speed is 100 miles per hour, which is perpendicular to the span length. And for example, the average difference base temperatures are -4 to 104 Fahrenheit degrees. Here is the result of the temperatures in the static wind pressure profile as a function of height. This example shows as the height of the tower, as the height increases, the wind pressure increases as well. Also, it shows the lower temperature values, the more the temperature is lower, the more is the impact of the wind pressure. Numerical models are also developed to verify these assumptions. Here is the SAP model of the south span of the bridge. You will see that worst moment demands happens for extreme temperature of -5 and 40 Fahrenheit degrees, based on the results that are shown here on the base tower. Also, the maximum deflections occurs at the top of the tower in the wind directions, and it shows and confirms that for lower temperatures, the maximum deflection is higher, which shows that we need some objective protocols to decide open or closed lift operations in case of extreme environmental conditions. The numerical models also can be used for calibrating purposes. Monitoring data can be used to calibrate numerical models. The step matrix can be optimized with monitoring data that are continuously monitored along the bridge. They can be used for design verifications and design protocol developments, also visual inspection planning, structural behavior predictions, and bridge management and decision making. This is the tidal energy conversion system, which is very interesting in this project, that helps us to convert tidal current energies to the energy that can supply the power of the sensors. Vertical guide posts and turbine deployment platforms are installed. However, the rotor of the turbine will be installed in October 2017, in the next few months. The scale model of the turbine is already examined in the ocean engineering department. They verified everything in there for the energy that can provide these sensors. Here you will see the current picture of the platform, which is attached to the pier of the bridge. As conclusions, we will configure that temperature and wind speed can significantly impact bridge system performance with respect to structural and mechanical considerations. The environmental data collected via the two weather conditions will create data-driven basis for bridge operations. The long-term data collections helps to determine if temperature and wind speed should be the basis for the suspension of the lift operations. And the combination of local model of the connection with the global models can be used to efficiently predict the performance of the bridge as a system. As a future work, we are going to collect lift structural response and mechanism performance during a range of temperatures and wind speed to provide decision-making protocols. We are going to optimize numerical models and calibrate them with monitoring data. We are going to evaluate the predicted impact of wind speed on the tower deflection and vibrations under different temperatures, and develop a response-based decision-making protocol for lift operations, and install the turbine rotor in the tidal turbine platform to power structural, environmental, and underwater instrumentations. At the end, I would like to acknowledge the National Science Foundations, Federal Highway and Discrimination, and New Hampshire Department of Transportation to support this project. And thank you for your attention.
Yeah, I just happened to notice on one of the slides you had an arrow pointing and you said pedestrian interference. I was just wondering, was it sensitive enough where you were looking at the effect of pedestrians on the bridge or not?
Well, actually, the pedestrian effects is coincide with barrier effects of traffic loadings. That's why its impact is significant.
I'm assuming that it's only looking at live load stresses. There can be no determination of dead load stresses?
No, that's for live load stresses. Thank you.
The preceding video was produced by the National Center for Pavement Preservation. More information can be found at tsp2.org. That's tsp2.org. Additional support provided by Michigan State University.